Now it started. I will begin with a word of prayer. All right. So let me begin. Dear Father, we thank you for this day. I thank you for these students. Just ask you help us to use this time wisely, just to wrap up our thinking before the test and just to review wisely, Lord. In your name I pray. Amen. So I've returned your quiz 4, 5, and 6. I graded them, which means that they weren't really graded. So I have to err on the side of caution, which means all of you have pretty good grades. Now, that does not mean that what you wrote is correct, right? I don't know. I'm not saying it's wrong. I'm just saying it's possible that you got a good grade on quiz 4, 5, and 6, and no, nothing. But
Can you grade like that in the exam?
grade like that on the exam? No, I will try hard not to do that on the exam. But there is a solution written for quiz 4, 5, and 6 posted in Blackboard, right? So you can look at that and see what was supposed to be done, and if you have questions about that, you can ask me. Let me, before I forget, do another cross-product example, just because I feel like you could afford to see another one of them. So, and then I'll take your questions about other stuff. But, so suppose we have a pivot point here, and then over here at the point 1, 3, and minus 2 in meters. Suppose at that point we apply a force. Suppose we apply the force F equals to, I don't know, how about minus 2 newtons, 3 newtons, 6 newtons. You're like, so are you going to write the units out to the right or inside the vector? I mean, either way. So to calculate the torque generated by this force about the pivot, what do we need to calculate here? Torque is what? Oh. We need R cross F, right? Torque is R cross F. Now, I haven't even pictured R, but if I was to picture R, it would be like this. So this is the radial arm, R. So what is R? I guess I need to tell you where the pivot point is. Where do you guys want to make the pivot point? I didn't label that point yet. What do you want to put the coordinates on the pivot point to be? 10, 20, 30? All right. So what's R equal to then? So apparently R is equal to minus 8 meters, minus 17 meters, and minus 32 meters. All right, so the torque is minus 8, minus 17, minus 32, cross product with minus 2, 3, 6. And the units out here are Newton meter. So there are various ways of calculating the cross product. I'm just going to do it this time, if you don't mind. Let's see here. So actually, so do you guys prefer in the solution I wrote to the quiz, I used a determinate mnemonic. Did you like that? You like that?
No, for the first part, is it 1 minus 10?
Oh, yeah. Thanks for telling me that now. I do appreciate that. Because if you told me that about 2 minutes from now, I'd be really annoyed. Thank you. Any other mistakes I've made. On purpose, of course, for the learning. Okay, so there are various tricks to calculating the cross product. Here's one that's popular. You look at the determinant of x hat, y hat, z hat, and then you put the first vector, minus 9, minus 17, minus 32 in the second row, and you put the last vector in the third row, minus 2, 3, 6. And this notation is just a reminder to do the following formula. It's x hat times minus 17 plus, well, I'll write it out, minus 3 times minus 32. And let me emphasize where those are coming from, okay? So what I did is I look at the numbers which are here and here. So these numbers go to make that up, all right? So it's the numbers which appear not in the x hat column and row. Then next, I do minus y hat times the things that are not in the y hat column and row. So I'll circle those in red. It's this and that. So what I do is I do minus 9 times 6.
Where's the 6 in the first one?
Did I not put a... Oh, yeah, that's a good question. I just made a mistake there. Sorry about that. Thank you. You're right. That should be minus 17 times 6. Thank you. My bad. So getting back to the second one, minus 9 times 6 minus a minus 2 times minus 32. It's, I'd say it's karaoke, but and provide any backtrack. So you're, and let's see here. So the z hat, everything that's not in the z hat column and row, so like this piece over here. So I get minus 9 times 3 minus a minus 2 times minus 17. Now, I don't know. I'm not entirely convinced that what I just did is really better than the formula I wrote down for you guys the other day. But anyway, here it is. Let's see here. And at this point, I need to get my calculator. Otherwise, I'm going to make a stupid mistake because you guys made these numbers big enough that if I try to do them in my head, I'm going to... Oh, there's just no telling what I'm going to do today. All right, what we got here? That's 6. I think I get this in red works out to minus 118, right? But then that minus gives me a total of 118 here. And then over there, we've got 27 minus 30, minus 27 plus a minus 34, I think. So I get a minus 61 over there if I'm not wrong. And of course, the units on this thing are Newton meters. So torque is a vector, and in this case, it works out to 118, and minus 61 Newton times Newton meter. Now, we can check and see whether or not we're right. If we've calculated the cross product correctly, we should be able to check our answer, right? So the torque should be perpendicular to R, and the torque should be perpendicular to the force. That's what the cross product formula is supposed to do for us. So what is the dot product of the torque and the radial arm? So we've got 118 minus 61, dot product with what was my R, minus 9, minus 17, minus 32. And that all, you got yourself a Newton meter squared from that. In terms of the units, I don't really care about the units, but what's that give me? Minus 54, minus 17 times 118, whatever that is, plus 61 times 32. So 2,000 minus 54. Man, you guys really made me work for this one. Minus, I should have made you give me smaller numbers. 2006. Goodness gracious. 61 times 32. Plus 1952. It's all very interesting numbers. Zero. So, and I'm lazy, so I'm not going to bother with the other one. But you can check that the dot product of the torque and the force is also 0, which goes to show you that we calculated it correctly. Now, listen, guys, you don't have to use this determinate mnemonic is fine, but I personally sometimes gravitate towards using, alternatively, you can use the following formula, like A cross B is equal to, well, let me use R and F. So the R cross F would be equal to, X, Y, Z crossed with F, Fx, Fy, Fz. And here's a formula for that. You've got Y Fz minus Z Fy, comma, Z Fx minus X Fz, comma, X Fy minus Y Fx. So alternatively, you could use this formula to calculate the torque, right? For example, if I was calculating the cross product of, say, 1, 2, 3, cross the force 10, 0, 7, right, in Newton meters, that would be, let's see here, Y is 2, so I've got 2 times 7, and then Z is 3 here, so minus 3 times 0. And let's see here, ZFX would be 30, and then XFZ would be minus 7, and XFY would be 0, and YFX would be minus 20. So as you can see, and of course the units would be Newton meters. And so I got myself a 14, 23 minus 20 Newton meters, which you can check is perpendicular to the two vectors there. Like dot product of 10, 0, 7 with that gives me 140 minus 140. Great. The dot product of 1, 2, 3 with this gives me 14 minus 46 minus whoa. Wait, what?
Over here. reason, I get negative 118 and a positive 61.
You said over here you got what?
6, negative 118,
Uh-huh.
and then positive 61.
Well, I don't think that's right. There's a minus here, and that minus compensates the minus. I mean, this minus is part of the determinant formula, which is part of the reason I'm not sure it's the greatest formula for you guys.
I got the same answer she did. I did it that way.
Oh, you got it that way.
Yeah.
You got, really?
Yeah, I got positive 6, negative, positive 61, but I did it this way. It has to be wrong too.
Well, I don't know. I mean, I got the dot product to 0 over there. I'd be unlucky. I mean, we can check the other one.
Why did you write negative 118 right there?
Because the thing in red works out to minus 118, but there's also this minus here, which minus minus gives me plus. Oh, that does not work out to 0? Oh. So, all right. All right, so it is. All right, let's see here. Where am I wrong? So Tyler is saying that you're saying the y and z components are fine.
I haven't double checked those yet. I knew the 6.
Yeah, it's negative.
-6, you say. All right. If that's a -6, and I agree with my check, I got over. If I put the minus here, then it's actually, when you check something, you actually need to check it, right? So this is a plus 54, which would be better, because then we have plus 54 plus 1952. We actually get 2006, which then works out to 0. So that one's. Let's. So I think what happened was when I did the purple arithmetic, I got confused about which number was bigger when I subtracted. Yeah. That's the way the determinant formula works. It goes plus minus plus minus. That's part of the advantage of using this formula is you don't have to remember that. Have I made a mistake over here as well? What's 20 times 7? 140, right? What's 2 times 23? 46. Yeah, this is not right. I've made an error here too as well. Where is it? So this is x, this is y, this is z, this is fx, this is fy, this is fz. So 2 times fz is 2 times 7 minus z, which is 3, fy is 0. Okay, fine. Z is 3, fx is 10, so 3 times 10, minus 1 times fz, which is 7. One times 0 minus y is 2, fx is, I got 20.
No, that's right.
That's right. Oh, I'm sorry. Well, I'm just having trouble getting the dot product of this. And I mean, I got the dot product of F and the torque seems to be 0 to me. That checks. But I'm having trouble getting 1, 2, 3. I mean, why is this dot 1, 2, 3, 0? Oh, I see. I'm an idiot. So minus 60 plus 46 plus 14, 0. We're fine. All right. Yep. That came off. How'd that come off? That's all right. All right. I think we're sort of okay. All right. Is the audio bouncing? La la la. All right. All right. So, listen, guys. The cross product, you can do it, but you have to be careful, right? As you can see, it's pretty easy to make a mistake in, I mean, because how many different, there's like 6 separate products involved in calculating the cross product, and each one of them comes with their own particular sign. So I think it's, I mean, I tell this every class in physics I teach, and also in my Calculus 3 when I teach it. It's so important, it doesn't take long to check your answers. To check answer, all you got to do is take the dot product of the alleged cross product with the 2 inputs. It should be 0. It should be perpendicular to both. Now, of course, here it's interesting to us because this describes the axis around which this force creates a twisting motion, right? So like what this physically means is if you apply a force like that to that point relative to some rod which is anchored at the pivot point, then you're going to try to like twist that rod around an axis which points in the direction of the torque. And anyway, that's that. So I will now shut up about that, and let's move on to other things. I'm going to go close the doors here while I'm at it before we get any additional, oh, you got that one, thanks. Before we have additional singing. Oh, wow. Cool. You guys are way ahead of me. Oh, man. Don't walk into the cloud. It's a bad cloud. Whew. Are you guys excited about break? Yes. Me too.
Will we have to wait until after break to find out our grades on this exam?
Yes. I'm pretty sure. I mean, the likelihood of me having these exams graded before break is pretty small. Pretty small. Ah. I mean, I guess I could just make the test like one problem, you know? No, it'd be one problem that involves all of the concepts we've covered, right? Reminder, you need to make sure you know your moments of inertia. Be sure you have these on your sheet, all right? I mean, I'll probably give them to you if you ask me on the exam, but it would be much more convenient for you to have them on your sheet, right? I mean, I generally speaking try to include that kind of information in a problem on the test, but in the event that I forgot, wouldn't it be nice to already have it on your sheet? I'm talking about table 8, yeah, figure 820. So the moments of inertia. All right, guys, you have questions about homework?
Number 29, page 223.
Number 29, page 223, I heard. Okay, good problem. All right, so we've got a some sort of rod, and I guess it's we're supposed to calculate the torque about the point C and then about the point P. Now, what forces are at work here? You've got 65 newtons at 45 degrees at the point C. You're also looking at a force of 56 newtons at 32 degrees here, right? And then down here at the point P, we've got a force of 52 newtons at 58 degrees off the axis of the bar here. We're supposed to determine the net torque on this 2 meter long the 2 meter long bar. And we're supposed to calculate the torque about the point C and then also about the point P, all right? I'm going to add something to that. Then find the angular acceleration in both cases. Find that, part A is about the point C, and part B is about the point P. So P is at the down here, and C is up there, right? And I think we should give labels to these forces, right? So let's call the top one F1. Let's call the middle one F2. Let's call the lower one F3. And let's also notice what's the deal. This distance right here is 1 meter, right? And this distance up here, also 1 meter, because it's a 2 meter bar, right? So halfway, 1 meter. Agree? So, all right, so let's work on part A. So we're going to have to calculate the net torque. It's going to be the torque due to force 1 plus the torque due to force 2 plus the torque due to force 3, right? And this is all about the axis. So you guys got to watch me. The axis given by the right-hand rule, put my hand here, think about wrapping around the axis like that. It's pointing out at you. So this direction is the counterclockwise direction. It's the positive direction for the net torque, all right? So which one of these forces is going to produce a positive torque? Not F1, right? F1 is it's going it's making a clockwise kind of torque, right? So F1's got to be minus. What about F2? You're applying the force at the pivot point. Yeah, that means that the radius arm is 0. The torque from 2 is 0. So that's kind of silly. So this one's just 0. And then, of course, okay, so let's get to the details here. Torque 1, so we're talking about the, R1, F1, sine theta 1. And I need a minus, right, because of the, you see why I need a minus there? And then plus R3, F3, sine theta 3, because this is the formula for the torque in 2 dimensions, right? We don't need the cross product in this context. But by the way, the magnitude of the cross product, if you didn't know this, the magnitude of A cross B, you know what it is? It's AB sine theta. So when you take the magnitude of the the r cross f, you get rf sine theta is my point. And we put in plus or minus here to reflect the clockwise or counterclockwiseness. All right, so what's R1 and R3 are both 1 meter. So that's kind of boring. What's F1? 56. Theta 1. And are these the legit thetas? What's that theta? Theta here, if you picture A and you picture B, then this is theta, sweeping from A to B, or B to A. So yeah, the thetas given are indeed theta between R and F, right? Because R1 is literally this vector, right? And this is R2. So if you can imagine extending that down like this and looking at F3 like that, then yeah, that's 58 degrees. So that is, in fact, the angle we want for that sine to take. So okay, anyway, sine of 32. And then plus 1 meter. What's F3? Oh, 52 newtons times the sine of 58 degrees. By the way, to answer my made-up question, we're going to have to give a mass to the rod. Without a mass, I can't answer my question, except symbolically. Nothing against that, but I wasn't looking to be symbolic for my question. All right, what we got here? 56. Oh, let me do 52. 50. Clear. 52 times sine of 58. I got 44.09. I get 14.42 Newton meters. So that's counterclockwise, right? So that's the net torque about C, right? About the point C. So to answer my made-up question, find the angular acceleration. How does the angular acceleration relate to the net torque? What do you guys want the mass of the rod to be? I like 10 kilograms. I'll take it. Why not? 10 kilograms. So we know that the net torque is equal to the moment of inertia times alpha, right? Therefore, alpha is equal to the net torque divided by the moment of inertia, which is 14.42 Newton meters. And what's the moment of inertia here? There's actually a big difference between the case C and the case P. See, the moment of inertia about C, we're rotating a rod about its center point, right? Which was what? 1/12 ml squared, yeah? It's part F. 1/12 ml squared. Yep. So 1/12 times the 10 kilograms you guys made up for me. Thank you. And what's L? Yeah, 2 meters squared. So what do we got here? Ooh, well, that's not too much. 4.327 radians per second squared. Does this make sense? Now, which number was this? I've forgotten. So did we get the answer to part A, what the book wants? Yes? All right, cool. Now let's answer part B. Of course, you can't check my angular acceleration since we just made up the mass and tacked that question on, but it's a good question to ask, yeah? All right, so for part B, net torque, again, is the torque from the first force plus the torque from the second force plus the torque from the third force, but this time about P, right? So what's the, look at F3. See, now F3 is applied directly to the pivot point. That gives you no leverage whatsoever, right? So the torque, the torque from F3 is just 0 because there is no radial displacement of the force as it's applied to the pivot point. So that is just straight up 0. And then, well, let's see here. And we draw the picture. Again, over here, here's my point P. If I look at over here to F2, I guess that angle is still that 45 degrees, that's still the right kind of angle. Now, if we, again, think about the rotation relative to the point P, and we define counterclockwise as the positive rotational direction by right-hand rule, axis pointed out of the board at you, what kind of torque is F2? Is it a positive torque? I think it's a positive torque, right? Because F2 is trying to rotate us that way, so F2 is positive. And what about F3? Looks like we still got the right kind of angle. No funny business there. But on the other hand, of course, this time that one's negative. I guess that's the same as it was last time, isn't it? So anyway, net torque is looks like minus R1 F1 sine theta 1 plus R2 F2 sine theta 2. I don't mean the same. The forces are the same, but the R's are different, right? So, and what I mean by that is, what's R1? Well, R1 is still minus 1 meter, right? 1 meter times 65 newtons times the sine of 45 degrees, and then plus 2 meters times, oh man, I can't do math. I'm wrong. And that was supposed to be what? Sine of, too close to the board. The sine of 32 degrees. So this is supposed to be torque 1. Torque 1 is based on F1, which was 56 newtons, right? Sorry, I've lost my... Yeah, let me just... Let's try this again. All right, so torque net. So R1 was minus 2 meters, because that's the distance that F1 is applied relative to P. 56 newtons, yeah, thanks. And then the sine of 32 degrees. And my R2 is 1 meter. F2 was 65 newtons. And that's at sine of 45 degrees. So the net torque about the other point, about the end point, is what? Did you guys get minus 13.39? Newton meters. So this is about P. So what's the of course the moment of inertia, excuse me, rotational, I'll get it eventually. Angular acceleration would be the net torque divided by the moment of inertia, which in this case is minus 13.39 Newton meters. And so the moment of inertia now is not 1/12, it's 1/3, because the moment of inertia of a thin rod rotating around its endpoint is bigger, because more of the rod is further away from the point of rotation, which makes it have a larger, in some sense, rotational mass. Isn't that, by the way, kind of interesting? The moment of inertia for a solid body, it's not intrinsic like mass. It depends on where you're rotating the body, right? A different rotational axis relative to the body gives different moment of inertia. So it's not, I mean, I say it's a rotational analog to mass, but that analogy only goes so far. Anyway, so 1/3 ml squared, keeping with your 10 kilograms, and 2 meters squared. What do we got? Huh. I think I get minus 1.004 radians per second squared. So there you go. So that would be a clockwise motion. The other one would have been a counterclockwise motion, right? About C versus that one is about P. Does this make sense? Okay. I like this problem. It's, it's not too bad. It's they could make it trickier. They could give you angles that aren't the ones you want to put into formulas, right? The way to make this problem more fun is to, instead of giving you this 58 degrees, give you like this angle, right? Just give you the angle that you're not supposed to plug into the sine, make you think. You guys like to think, right? You're university students. University students like to think. You pay big bucks to think here, right? Your parents pay big bucks for you to think here.
Yeah, my parents are.
You're in debt to be, I don't know, something here. Some way or another, you're here. Your scholarship, right? Some of you are running in circles to be here, right? Or in a line, or swimming, or something. I don't know. What's that?
Nothing.
Oh, nothing. Are we done? Okay. Fine. Yes. Oh my. Yeah. Let us not forget. This test is on what? Momentum, energy, and rotational motion, right? I've been talking a lot about rotational motion lately, but that's just because, that's what we've been. So, which question?
Page 167, number 73.
Ooh.
Yes.
What's happening? Page 167, number 7.
All right. A 36 kilogram crate starting from rest 36 kilogram crate starting from rest, pulled across the floor with a horizontal force of 225 newtons. For the first 11 meters, the floor is frictionless. Ooh, I like this. I'm starting to like this already. 11 meters, frictionless. And then for the next 10 meters, the coefficient of friction is 0.2. All right. The question is, what is the final speed of the crate after being pulled these 21 meters? Ooh, I like this problem. This is a great problem. Wish I'd picked this problem out. Oh, I did pick this problem out, didn't I? Let's see here.
What is the final, what was the question?
What's the final speed of the crate?
Oh, well, what are you the question?
Let's see here. So, what's the right approach for a problem like this? I mean, we know the work energy theorem, right? So if we can calculate the net work done on the box during the motion, then the net work is equal to the change in kinetic energy, which should allow us to calculate the final velocity. So what's the work done here? I say the work is equal to the work stage 1, yeah? Plus the work in stage 2. One of these is very straightforward. So the work in stage 1 is just 225 newtons times what? 11 meters. Because the force is horizontal and it's being applied in the direction of motion, so we get to go back to middle school and say work is force times distance. Middle school, right? Preschool? No. Not in this country. Maybe not in any. Maybe on Vulcan. I don't know. Vulcan. You know, the planet where Spock comes from. All right, let's see here. You guys know about Vulcan, right? Okay, and then over here, the work in stage 2. Well, you know, there's still 225 newtons, right? And so that force is still developing, doing work. So we've got 225 newtons times 10 meters, right? But then there's something else going on in the last bit, right? Yeah, friction. Friction. So like here, you know, yeah, you've got the 225 newtons, but you've also got the force of friction. What's the force of friction equal to? Mu k times the normal force, right? Which in this case is 0.2 times mg, which is 36 kilograms times 9.8 meters per second times 0.2. What is that? I get 70.56. That's the, so we have to subtract the work done by friction because, I mean, we subtract the energy lost to friction really, which is the negative work. It's minus 70.56 times what? What distance is that force of friction applied over? Just the last 10 meters, right? So 10 meters. So this should give me the net work that's done in the entire motion, which is what? Let's see here, 225 times 21 minus 70.56 times 10. I get 4,019.4 joules. Now that's equal to the change in kinetic energy by the work energy theorem. So that's 1/2 m Vf squared minus 1/2 m V naught squared. But good news, V naught is 0. So Vf squared is equal to 2 times 4,019.4 joules divided by 36 kilograms. Solving for Vf squared, what's that? I get 223.3 meters squared per second squared. Therefore, the final velocity is 14.94 meters per second. I like this problem. What chapter are we in? 6? Yep, 14.9. Now, is this the only way to do this problem? Absolutely not. You could use a kinematic approach, right? You could figure out the acceleration in the first 11 meters, right? The acceleration would be 225 divided by 36, right? The force divided by m would give you acceleration. And then you could figure out the final velocity at the middle point using kinematics. And then you could figure out the net force in the second thing, find the acceleration, solve the kinematics problem, and then sort of daisy chain those two together to figure out the final velocity. But I think we can all agree that using the work energy theorem is like logically much less trouble, right? One of the things you should be thinking about for the final is some of the problems that I asked you on test 1, you now have a better way to solve, right? Conservation of energy for projectile motions is much nicer in some sense than just direct kinematics, the direct kinematic equations. So, but everything we knew on test 1, we still know on test 2, right? So you still need to know how to build your way from velocity to position to acceleration when it's constant and so forth. Other questions? 83. On 227. Ah, no, you're making me go back to, you're making my head spin again. Let's see here. Number what would you say? 83. 83. Oh my goodness. Ooh. Exciting. A hollow cylinder, aka a hoop, is rolling on a horizontal surface at a speed of 3 meters per second when it reaches a 15-degree incline. How far up the incline will it go? And how long will it be on the incline before it arrives back at the bottom? Ooh, I like this. This is a great problem. I like all these problems. Oh, it is because I chose them. That's true. That is true. I also like physics, so there's that. But that is one distinct advantage I had over many of my peers in school, is that as a physics major, we like physics. Liking something is a tremendous advantage. It's true. Let's see here. Oh, it's not always true in relationships. Sometimes if you don't like someone, you've got a better chance of attracting them, right? Depends on the person. So we have a hoop, and it is rolling at 3 meters per second. Reaches the 15-degree incline. The question is, how far up the incline will it go, and how long will it be on the incline before it arrives back at the bottom? Now, I don't like the wording here because there's two different ways you could interpret how far up the incline it will go. Probably what the textbook means is the actual distance parallel to the incline. So probably they're asking for, but you know, if you're not sure about what I mean by wording on the test, you should just ask me if that kind of thing happens to rear its ugly head. But I think this is what they mean. All right. But I could see a student reasonably interpreting it to mean this distance as well. Yeah. I don't know which one. You guys say it's D. Good. So I'm just the weird one to think it's H. Good. Now, how do we solve this problem? Conservation of energy is the way to go. So what kind of energy does this hoop have? It's rolling without slipping, right? What's its mass? Do we know? Oh, it didn't tell us the mass. Ooh, exciting. So the kinetic energy is equal to kinetic energy translational plus the kinetic energy rotational, right? And so this is at the initial, right? And how about the end point here? Well, that's equal to the potential energy at the end, right? Which, by the way, would be mgh. Why is there no kinetic energy at the end? Well, I'm interested in the point right before it starts coming back down, right? So right when it's at rest at the top of its, up the incline, yeah? So, okay, translational, that's 1/2 mv0 squared. How about rotational? That's 1/2 I omega naught squared. Now, what is the moment of inertia? What's I here? It is mr squared, right? Because all of the hoop is distance r from the center point, right? Hey, and so this becomes plus 1/2 mr squared omega naught squared, right? Ooh. Hey, the m's are canceling. That's nice. And hey, what's r omega naught? If I take the radians per second and I multiply by a radians distance, what do I have? I've got I've got the meters per second, right? This is exactly v0. Again, that assumes rolling without slipping, but they've not given us any reason to think otherwise. And, well, there's also the fact that we've never discussed the physics of rolling with slipping, so that kind of rules that out. You know, yeah. So cancel the m's. This is really v0 squared in disguise. So what you got here? 1/2. Looks like you got v0 squared equals to gh. So therefore, h is equal to v0 squared divided by g. Yeah. Which is 9